We're going to practice applying the mechanical energy balance by thinking about a fairly mundane activity, which is the running water coming out of a faucet. Now, turning on a tap of water is something I hope you see every day of your life. But even though it is a mundane activity, there are some fairly interesting physical phenomena going on. And in particular, one thing I want to point out in this example of a picture of an open faucet, is I want to focus on the sort of radius of the water stream that's coming out of the faucet tap. All right? And so you can see here that when the faucet comes out, or when the water comes out of the faucet tap, it has a radius or a diameter that's about that big, right? But as you go down the stream, you could see that radius becomes smaller and smaller. The stream becomes thinner, right? And so, why does that happen? Why is our stream changing radius as it falls from the faucet tap? And so what I want you to do here is I want you to pause the video and I want you to kind of think about reasons for why this would happen. So the main reason that the radius changes as the water falls from the faucet tap is due to gravity. All right? And so to show you this, I drew this little schematic here of water coming out of a faucet tap. Okay? And what I want you to consider is the water at point Z1 here, which is right at the tap opening. Let's say that water is coming out at some velocity U1. Now, as the water falls from the faucet tap, right, the force of gravity is causing it to move faster, right? And so, by the time it reaches point Z2 here, the velocity, U2, is greater than the velocity U1. Because of gravity. Okay? Alright? But that still kind of doesn't directly answer our question. Why does the radius change at the different points in the stream? Alright? And to quantitatively figure out that relationship, what we're going to do is we're going to use and apply the mechanical energy balance so that we could get a description of the radius of the stream as a function of the distance away from the faucet tap. And so what we're going to do is we're going to find the radius of stream at some arbitrary point Z2 in terms of other variables. Alright. And so the way we're going to approach this is let's first actually just start with the mechanical energy balance. So I know this is breaking our typical approach, but I just want to start this way for pedagogical reasons. Okay? Alright, and so what I want you to do first is I want you to write out the mechanical energy balance equation that we derived in the previous video. And so we have our delta P over density plus the change in velocity plus the change in height is equal to, or plus the friction term is equal to the shaft work over the mass flow rate. Okay? At this point, what I want you to do is to pause the video, and I want you to think about the terms in this mechanical energy balance that are negligible and that you could cancel out. Alright, let's go from left to right. And so starting with the pressure gradient term, we have to remember, in our system, and it probably helps out if I draw the boundaries, what we're considering is the stream from Z1 to Z2. Okay? And so, if you just consider a normal faucet tap with water coming out, the pressure at Z1, probably atmospheric pressure, and so the pressure at Z2 is also going to be atmospheric, right? You know, the height we're looking at isn't going to be so drastic. All right. In any case, because pressure 1 is equal to pressure 2, that means that we don't actually have a pressure gradient here. And so this is going to be equal to 0. All right. And so I'll write it out here. Pressure same at Z1 and Z2. Okay? All right. The next term deals with velocity. And as we said, U2 is greater than U1 due to gravity. So that term will stay there. All right. In the change in potential energy, right, we're looking at what happens at two different heights. So we need that term to be around. All right. For the frictional term, you know, we're not really considering the role of air friction here. And so for now, let's just cancel that out. All right. And for shaft work, we don't have any moving parts. Right? We're just looking at water falling from one height to another. So there's not going to be any shaft work here. Okay? And so the only things we're considering are the change in the velocity and then the change in height. And so let's expand out the kinetic and potential energy terms. And so what we have is U2 squared minus U1 squared divided by 2 plus G Z2 minus Z1 equals 0. Okay? And if we rearrange the equation, we can now describe the velocity U2 as a function of everything else. Okay? And so now we have this equation, which I'll call equation 1. So that's fine. But this still doesn't get to our goal, which was to find the radius in terms of Z2 and all the other variables. To get that relationship, what we're actually going to turn to is our material balance. Right? And so, from our material balance, what we could say is that the mass flow rate at point 1 is going to be equal to the mass flow rate at point 2. Alright? So, those are the mass flow rates. But since we're dealing with liquids and stuff, we could rewrite the mass flow rates in terms of the density and also the volumetric flow rate. Now, in our system, what we're dealing with is falling water, right? And because this is a liquid, we could assume it's incompressible. And so that would mean that the density at point 1 and point 2 are essentially the same. So we could cancel those out. And what we're left with is that the volumetric flow rate at point 1 is equal to the volumetric flow rate at point 2. Now, you know, we don't have anything, we don't know what the volumetric flow rate is. But fortunately, what we could do is we could rewrite the volumetric flow rate in terms of the cross-sectional area of the stream and also the velocity of the stream at point 1 and point 2. So what I mean by that is we could say the volumetric flow rate at point 1 is equal to the area of the stream, cross-sectional area of the stream, times its velocity. And the cross-sectional area of the stream, so what I mean by that is this little circle thing here. The cross-sectional area there is just going to be equal to the area of a circle, which is pi r1 squared. All right? And then that's going to be multiplied by the velocity at point 1. We could do the same thing for the volumetric flow rate at point 2. All right. And so, from our material balance, we know that V1 is equal to V2. So we could set those things equal to each other. Cancel out the pi's, and we could rewrite the equation to describe the radius 2 to be equal to R1 times the square root of U1 over U2. But earlier, we derived a relationship for U2, and so we could plug that in. So now what we have is U1 divided by U1 squared minus 2G Z2 minus Z1, and all of that to the 1/2. Right? And so now we have a relationship between the radius of the stream at point 2 and all of the other variables. And we were able to achieve, and there should be another 1/2. Should be another 1/2 here. Right? And we were able to derive this relationship by just applying, don't need to box it in now. We are able to derive this relationship just by applying the mechanical energy balance.